Okay, knowing that P, the transition matrix, is equals to those things, now we can prove why Metropolis Hastings actually works, right? Why this give us the Markov chain that our target distribution is a stationary distribution, right? So all we need to do is to prove that fx times pxy for any xy this always equals to fy times pyx, right? If we can show this is true, then we actually prove that f is the stationary distribution for P, for this Metropolis Hastings Markov chain, and this P Metropolis Hastings Markov chain is time reversible. Remember, that's how we define a time reversible. Like in this case, this is an example of time reversibility from what we learned before, that if a probability mass function mu on the state space S of a Markov chain satisfies mu I times Pij equals to mu j times Pji, then if this is true for all the I and j, then mu is the stationary distribution for P, and P is the time reversible Markov chain. Right, that's what we learned before. So we're going to prove that. We're going to prove this. So fx times pxy equals to, you plug in what is pxy, okay? Because in this case x not equals to y, right? And you plug in here, and then we can multiply fx times qxy inside of this minimum, right? Because all the f and the q, they all probability, so they all positive. So we can multiply this inside, and we got this whole thing. And that's clearly that you can switch x and y, right? Because there's no order for the minimum. So you can switch those two, and you got exactly fx times pyx. Okay? So now we prove that this equals to this. So we actually know that this is a sufficient condition for f to be a stationary distribution for P. And we also know P is time reversible.